I was a child, children began to come outside of the Eastern Bloc. And I remember it was a big shock because when I saw that Mr. X invented the telegraph, I heard it was invented 100 years earlier in the Soviet Union. And then someone A did this.
Like Popov.
They always had it. For any name that I had, they had another name who did it before, rigorously. Okay. On the other hand, as hard as it is to admit, I think the field of cosmology was really worked upon in the Soviet Union before it was worked in the West. And the main important works were done there. And Slava was one of the pioneers of working out these things and their consequences. So we are very happy to have such a leader here. Thank you.
Who invented telegraph? Okay, good. So, what you see, in 1980, when I started to work in cosmology, before I was pure astrophysicist, so I know only gas dynamics and hardly could distinguish creation operator from annihilation operator, yeah? Of course, nobody was taking this thing seriously, and I don't know you are aware or not, but at 80s, the people who were interested in cosmology, at least in Russia, by some accident, or maybe not accident, were the creators of Russian nuclear and hydrogen bomb. Zeldovich, mostly, then Sakharov, Ginzburg partially. Ginzburg was my advisor. But of course, for these people, it was okay, because they did something already in their lives. Therefore, after that, they could have fantasy. Then, in the 80s also, not so many things were known about our universe. Of course, people knew that it's expanding. There is background radiation. And then, by the way, but it was not even known that universe really homogeneous and isotropic, or we are living somewhere in the center of spherically symmetrical universe somehow. It was so-called cosmological postulate. Now a lot of things are established, and mostly these things are established because of this measurement, okay, which happened during the last 20 years of the fluctuations of microwave background radiation. Moreover, in distinction from astrophysics, cosmology is physics. In which sense? You know perhaps what is the difference between astrophysics and physics? Or you don't know? You see, astrophysics is eternal science. Why? Because systematics there is never under control, and you always need some bosses who will tell you how to reduce these systematics. And you know what is systematics? Also, systematics is something, okay, what influence your experiment in a regular way. One of the examples are these TGV trains, I think. As far as I remember, they were influencing somehow measurement on lab. But if you know schedule of TGV trains, you can, of course, remove this systematics. So CMB measurement, as a measurement where systematics is under control. And because of this measurement, we know now several established facts about universe, and I will start telling facts, okay, which we know about our universe, and then after that, I will show you some movies from which it follows these facts, and then we'll go to explanation of this thing. So what we know? First of all, we know that our universe is homogeneous and isotropic in scales larger than 100 megaparsec. Now, I don't know if this auditory people know or not, but 1 parsec is about 3 light years, and 1 megaparsec is, of course, 10⁶ parsec. Now, we also know for sure that our universe, in spite of the fact that some people doubt it, but okay, we, normal, reasonable people, know that universe expands according to Hubble law. Yeah, okay, so Oh, this is much better. So now, these are facts which concern so-called dynamics and logical structure of the universe. What we know about matter composition of our universe? Now, we know that universe is pervaded by thermal radiation with a temperature which is 2.73, and there are two more numbers here, yeah, Kelvin. Now, we know that approximately per 1 billion of photons, there is 1 baryon. So there is baryonic matter. So 1 baryon per 9 photons. And because, as you know, photons, the number of photons is the same thing as an entropy, people speak about very high entropy in our universe. We know chemical composition of this baryonic matter. Namely, we know that 75% of all baryonic matter is just normal hydrogen, 25% is helium-4. And plus 10 minus something, for instance, small trace amount of the other element. In particular, we have 10 minus 5%, not percent, 10 minus 3%, 10 minus 5 deuterium. Then, of course, we have heavy elements, but all these heavy elements were born in the explosions of supernova and in stars, so they are not so interesting for cosmology. Now, second thing which we know since recently, that baryons constitute only 4% of all matter in the universe. 96% is dark. And this dark matter, or not matter, this dark component of the universe, which we do not see directly, okay, in some other interactions, but nevertheless, we see this thing directly in gravitational interactions. Therefore, when people say that this dark matter was not yet found, it's wrong, because we found it, okay, via gravitational interaction of this matter, but it was not found via other interaction of this dark matter. So this dark component also is not homogeneous. It consists of so-called 22% of dark matter and 74% is dark energy. What is the difference between dark matter and dark energy? We know that dark matter has pressure which, from the point of view of general relativity, is approximately equal to 0, and this dark matter can cluster. Dark energy, in distinction from dark matter, has different equation of state, namely pressure for this dark energy is approximately equal to minus energy density, and this equation of state corresponds to so-called cosmological constant. So it's homogeneous and cannot cluster. Moreover, dark matter, gravitating matter, and dark energy is anti-gravitating matter. Dark energy, as you know, also was discovered. Moreover, it was discovered in this supernova observation, but supernova observation, as you understand, astrophysical observation, and if people would see this thing only in these supernova observations, nobody would give Nobel Prize for this dark energy. But the fact that dark energy exists was proved again from the measurement of cosmic microwave background radiation, where everything is under control, and without dark energy, you could never explain these nice pictures which we have in this measurement of the fluctuation of the temperature. So this is what we know about present state of the universe. Now we could ask question, what we know about past of the universe, and In fact, we have direct photograph of the young universe when it was 1,000 times smaller than it's right now. In which sense 1,000 times smaller? Of course, universe can be infinite, but 1,000 times smaller just means that the distance between, for instance, two objects which we see right now in our universe was 1,000 times smaller than it's today. So we have direct picture of this very early universe, and we know that when the universe was 1,000 times smaller, then there was no galaxies, no planets, nothing. Universe was extremely homogeneous and isotropic, and energy density could vary from place to place only by the factor 10 minus 5. There was small inhomogeneities, which at the end led to this kind of large-scale structure which we observe today. You see, namely, clusters of galaxies, then stars and planets. And in fact, it's very easy to understand how these small inhomogeneities led to these big inhomogeneities which we see right now. This happened as a result of gravitational instability. In those places where there was a little bit more matter, gravity was larger, and it was attracting more and more and more matter. And finally, we formed these nonlinear structures. Moreover, we know detailed spectrum of these inhomogeneities, which we got measuring this fluctuation of background radiation. Why? Fluctuation of background radiation delivers this picture, about very early universe. Because this radiation decoupled from the rest of the matter at the moment when universe was precisely 1,000 times smaller than it's right now, and after that, this radiation was propagating without any scattering, thus delivering us very time-retarded photograph of the early universe. So, and now let me show you a couple of movies, which, where I will present this experimental result. I think most of you technology failed. No? Okay. It worked. So as you know, you see in the sky stars. Typical distance between the stars is about few parsec, yeah? Then, all these stars we can see without telescope normally belongs to our galaxy. You perhaps know it's very easy to memorize that in typical galaxies about 100 billion stars. Now, then, it was discovered that there are, besides of our galaxies, there are a lot of other galaxies, and this is one of them, yeah? You see, which has very nice structure, but of course the number of these galaxies is really huge. It's also very easy to memorize how many galaxies do we have in our universe. It's again 100 billion galaxies. So you can easily remember this thing if you know how much Bill Gates made on these windows. You see? After that you will not forget about it. Then, these are direct pictures. And in fact, I remember that in 1980, the dream of astronomers was to take redshift of more or less full sample of galaxies which would consist of, say, 5,000 galaxies to be sure how matter is distributed in large scales. Because I remember very famous Russian astronomer, Karachintsev in 80 just didn't believe even in existence of clusters, which Zwicky has seen on the photographs or photoplates of this Palomar telescope, because you could see not, I decided that perhaps I'm not good astronomers because on these photographs I couldn't find any single galaxy. And Zwicky was able to find actual clusters where there was about 50 galaxies together. Karachensov was saying that it was accident because all these galaxies are far away from each other, but they came close to our satellite. Now, of course, after that, technology was developed quite a lot, and finally, you see, we got in Sloan digital survey this nice picture where every point corresponds to the galaxy. So it consists of 100 billion stars, every point here. And people were able, just with computers and one telescope, which was 2 meters, take redshift of 1 million of galaxies. So finally, and if you know redshift, you can put them in the appropriate point in the space. And finally, there was established that our universe is really homogeneous. Moreover, people have seen the structures here. And the structures were, as you see here, like clusters of galaxies. Normally, it consists of many galaxies. 2 clusters of galaxies are related with so-called connected by filaments. Filaments are connected by domain walls, and between these walls we have a lot of empty space. You see, so all this structure forms here so-called web-like structure of the universe. This is what we have today. Now, if you would take and would smear, for instance, this distribution of the galaxies over the scale larger than 200 megaparsecs, then you would nevertheless find that everything is homogeneous and isotropic. After that, when you go in past, when radiation was decoupled, you are getting this nice picture, and different colors here correspond to a little bit different temperature on the scale. So variation of the temperature from one place to the other, which correspond to the different colors, correspond to this number 10 minus 5. And from here, yeah.
I don't understand, because you have these columns, so how is that homogeneous?
No, but you see, homogeneous means that when you take, for instance, one box, there are these clusters, yeah? Then you take box with the size 200 megaparsec, yeah? And the other box, then you will find that the amount of matter there is approximately the same. So you have to smear the thing at present. But in past, you don't need to do even this thing, because as you see, temperature varies from one place to the other by 10 minus 5 factor. And these fluctuations of the temperature are proportional to the energy density in the appropriate place. Of course, this picture is two-dimensional picture, but nevertheless, after that, you make simple assumption, which is, by the way, in agreement with the fact that today universe is homogeneous and isotropic, and then you are getting the whole spectrum, or the whole picture. And moreover, because measurements here are extremely precise, you could measure so-called power spectra of the temperature fluctuation. So you can measure how, delta T over T, for instance, variation of the temperature for the given angular scale depend on the angular scale. And after that, there are predictions of the theory from inflation, about which I will speak later, for this kind of fluctuations. And there are measurements, and let me just, so I will skip this thing because I will talk about it anyway. Yeah, so you see, there is the picture, which is theoretical prediction. Of course, there are certain parameters, and there are experimental points. By the way, I think you do not see here points, which come precisely on this red curve. It's point from WMAP experiment, which was excellent experiment, by the way, made with perfect price to performance ratio. But this WMAP experiment went somewhere up to here. Now there are 2 other excellent experiments, ground-based experiment, which measure power spectra of the temperature fluctuations. Here is multiple moment, and angle is inversely proportional to L, of course, and here is a typical amplitude for the appropriate angle. for the temperatures in two different directions. And here are the results which were obtained on this Atacama cosmology telescope, where Lyman Page was principal investigator, and also on South Pole telescope. And you see, they come in perfect agreement with this red curve, which you draw, okay, just deciding parameters of the theory. And you see all these little peaks up to peak number 9. So this actually, I can tell you, extremely impressed experimentalists also, that all these points are coming there. Then I do not know, you know or not, but there was, by the way, about 70, I think counted about 70 experiments for measuring these fluctuations. There are so-called ground-based experiments, where everything is located on the ground when people measure this fluctuation. There are balloon experiments, like Maximum Boomerang, by the way, who gave us first good results here before WMAP. And there are most expensive experiments, satellite experiment, yeah, space experiment, and for instance, one of them was WMAP, and the other, we just flew 2 years, 3 years ago, and already collected all the data and had sensitivity 500 times better than WMAP. So these guys needed only 2 days, okay, to get the same result as WMAP was getting during 2 years, you see. And which supposed to give here even more precise measurement. So, but the main thing, perhaps here they will improve accuracy by factor few, and the main thing which will come from Planck experiment is more precise point in the region of third Doppler peak. By the way, this is the thing which we are missing for decreasing error bars on the predicted calculated spectra of the, how it's called this, quantum fluctuations from inflation. Besides of this measurement, there was done also measurement of polarization of this radiation, because you see, if you will take this radiation and would look it through polarimeter and will turn polarimeter, then, okay, brightness of the things which you see in a certain direction would depend on the angle under which you will turn your polarimeter. But nevertheless, this brightness will be varying only, for instance, by, for E component of polarization, by the fraction 1/10. You see? So you have fluctuation at the level of 10 minus 5, and polarization you should measure if you want to see it, and it's predicted at the level of 10 minus 6, E component of polarization. Moreover, this polarization is already measured. I didn't show it here, but it also comes nice in agreement, but nevertheless, points are not so perfect on this theoretical curve. What Planck would allow to do us, Planck would allow also to measure polarization with unbelievable accuracy for E component, where you could see even 3% variation. Error bar will be so small, 3% variation of the how it's called, of this polarization in the region of multipole 1000, which are due to the fact that you have not enough statistics, because within our universe, for multiple thousand, as you can imagine, you are getting about 2001 sample, and then from this 2001 sample, you have to make statistics, because all predictions are of statistical nature. Moreover, people try right now to measure, I will explain what is this, so-called B component of polarization. Why it's so important? Because this B component of polarization in large angular scale can have only one origin. It could be due to the gravitational wave, which could be produced only on inflation, on the stage of earlier cosmic acceleration. But this B component of polarization, which is expected, is at least 10 times smaller than E component of polarization. So you have to have measurement of delta T over T at the level of 10 minus 7. So you can imagine. But detectors are so sensitive that people, in principle, promise to do it within the next couple of years. Of course, there would be good to have satellite, but satellite would cost, in this case, 1 billion, and nobody would give 1 billion for one task experiment. You see, in spite of the fact that there is actually some application in ESA where they tried somehow to make multitask experiment. You see, but there will be balloon measurement where people will cover the range of the multiple about 50. And if we will be lucky, then perhaps in this spider experiment, people will find it within next 2 years. If we will not be lucky, then we can forget about it, but it's not tragic. So let me concentrate on the other things, not on big component of polarization, and let me try to explain, okay, how one could describe this measurement. Also, it will not go about galaxies, which are very nonlinear structures. You know that, okay, everything what we will need to do, we will need finally, or my final goal will be to derive this kind of curve, which is linear physics, where everything is under control, you see, and which is real physics. When we go to large-scale structures, or to galaxies especially, with a lot of gas dynamics, that will become very messy thing, actually, with a lot of systematics. But here, everything is very simple, and, okay, let me try, okay, during the time which I will have, not just today, but also during next several lectures, to convince you that, okay, this curve tells us that all of us originated from nothing, from quantum fluctuations. And this is the only useful place where perhaps quantum gravity, in its simplest form, as a linear perturbation theory, is relevant, you see, but nevertheless, it's an important thing, actually, as you know. And, okay, I will show you how to get tricky details of this kind of thing, which were found and which were measured with high level of, I think, accuracy, and also, okay, were proved at the level of 3 sigma, but 3 good sigma, okay, David, on which experimentalists, because when actually they found this sigma for the deviation of spectral index, I asked Lyman Page how much he would put on sigma, but not from grant, but from his personal money. And when I got answer many thousands, then, okay, I realized that it was serious sigma. No, because you see, you can compare Toft had bet with Hawking about Hawking temperature. It was $150 bet. You see, and was unresolved, I think, because nobody wanted to pay. So, okay, now let me switch to the blackboard and let me begin with some kind of elementary things which perhaps you know, but just I will refresh your memory, and I will need light here. Okay, so as I said, if you will take, yeah. By the way, do I need microphone or not? Huh? Because I can speak louder, otherwise I have to suppress my voice.
Turn off the projector.
Huh? Number 6, okay, good.
Closer, sorry. Yeah.
Ah, this one, okay, very good. So, okay, now let's ask question. Let's forget about all inhomogeneities and let's ask how to describe homogeneous gravitating universe. Yeah. So, assuming that universe is homogeneous and isotropic means 2 things. Homogeneous means that if you go from one place to the other place, then you will find exactly the same condition in the other place as in the place before. Isotropy means that you could look in different directions and you will see the same picture. Does homogeneity mean isotropy? Of course not, because, okay, universe can expand in one direction, be homogeneous, and contract in the other direction. Does isotropy means homogeneity? Also not, because you can be in the center of inhomogeneous but isotropic distribution. But if you would say isotropic at every point, then of course you would get homogeneous isotropic thing, yeah? It would be the replacement. Now, what are the examples of homogeneous two-dimensional spaces? Let's start with 2 dimensions, then generalize to 3 dimensions. I don't want to stay always in 2 dimensions. So, you know, simplest example is just plane, yeah? The other example is the surface of the sphere. There is one more example, which actually you cannot embed so easily in 3-dimensional Euclidean space, but you can do it, get it very easily, actually at the formal level, yeah? Is so-called Lobachevsky space, the space of negative constant curvature. Now, if we will forget about more complicated things, then these 3 examples are the only example which we have. And in principle, if you want to describe homogeneous isotropic universe, you could use only these 3 geometries. And the only law for the evolution is Hubble law. How to understand it very easily? Okay, let's take for simplicity the surface of the sphere of radius r. And let's take 2 points here on this surface. Yeah? Let's now assume that radius depends on time. It's clear that if you will not deform this surface, everything will remain homogeneous and isotropic from the point of view of 2-dimensional guy who lives on this surface. Now, let's take 2 fixed points here, A and B, and find how distance, if radius, for instance, of this ball is increasing, how distance between these 2 points is growing. So its radius multiplied by the angle, which stays constant here, right? Now, when you want to calculate the relative velocity of these 2 points, you just take time derivative of the distance, which I denote by dot, and you will get that this thing is A dot divided by A, I divided and multiplied it by A, theta AB. But theta AB is nothing more than just distance. So you see, 2-dimensional Hubble law tells us that the relative speed between 2 points is proportional to some function which depends only on time, and which is time derivative of the radius of the ball divided by radius, and called Hubble constant, multiplied by physical distance. And this is the only expansion law which is compatible with keeping homogeneity and isotropy at every moment of time. It's very easy to generalize this thing for 3-dimensional case. You just write between 2 points, okay, distance as scale factor multiplied by the constant of integration, which is analog of this angle and which is called comoving distance. And from here, you immediately get that, okay, relative speed between 2 points, so 1 point escape from the other point with a relative speed, which is ht multiplied by the distance dAb between these 2 points, where ht is nothing more than just A dot over A. You see? So this is so-called Hubble law, and then also you understand that when this law is satisfied, and you say that each galaxy escapes from me with the distance which is proportional, with the speed which is proportional to the distance to this galaxy, it doesn't mean that I live in the center of the universe. It means that for each point here on the surface, you have the same law. This thing is called Hubble constant, but in spite of the fact that it depends on time. Why it's called Hubble constant? Because, okay, at the given moment of time, it doesn't depend on the distance, and also it's changing on the scales 10 billion years right now, and nobody lives so long to see that it's changing. So, but nevertheless, it's constant up to this extent. Now, if we know that the universe is expanding, we can forget about gravity and can estimate immediately the age of our universe. Let's say that the measured quantity today is A dot over A, okay? And let's find the age of the universe. Let's make Russian style calculation. Okay, so cancel A here, then we will get 1 over T here. So from here you immediately see that T is of the order of 1 divided by H0, which is measured. And first it was measured by Hubble, who discovered this red shift in the spectrum of faraway galaxies, yeah, and interpreted it as a Doppler shift, which is due to this velocity. You see now, Hubble found for the Hubble constant the value 500 kilometers over second over megaparsec. I am sorry for these obscure units, yeah, but astronomers use them. I will be using later units where C is equal H, is equal KB, is equal G, is equal 1. But let's leave it, okay, for later things. Now, if you would take this value of the Hubble constant and estimate the age of the universe, then you would get the number which would be about 1 billion years, which is less than our universe, our Earth exists, as you know. Now, why Hubble got this thing? Because of systematics. You see how you measure distances normally in cosmology. When something is far away, you take so-called standard candle. You assume that some object has the same luminosity. Then you can measure distance, okay, because you know apparent luminosity which you are measuring, you see, and you can measure also speed, v, because of redshift. But you can easily make mistake even if sample is homogeneous, because you do not know what is the real luminosity. So Hubble made mistake by factor 10 because of this systematics. Then the question about Hubble constant was biggest headache, okay, for 40 years perhaps, since 70. Because there was two groups, Taman and Sandich and Vakuler. And one group was given value 100, and the other group 50. Okay, because series didn't know what to take, they were taking 75. Now, this Hubble constant was recently measured. By the way, you can measure them just from this curve also alone, with good accuracy, but not excellent accuracy, again, without systematic, and it was found that it's about 72 plus minus 3, you see? So, as usually, theorists were right at the end. But most amazing thing, by the way, when there was supernova measurement of the Hubble constant, then again, recently, some people were given 60 plus minus 3, and the other group was given 75 plus minus 2. So you could ask how actually you can reconcile this result. Again, systematics, as you know, because these kind of things didn't mean too much. So, as I told you, systematics is a disease of astrophysics, but what one can do? If you cannot do things better, then you have to live with disease. Fortunately, it's not cosmology. Now, next thing. If you are in general relativity, you know that the space is curved irrespectively. For instance, Mr. Mill liked it or didn't like, because Mill hated the fact that space is curved. Therefore, he invented some kind of other model where he had particles not interacting, just, okay, escaping from each other in our Minkowski space. But now it's irrelevant. What is the geometry? Yeah.
Maybe I have a question.
Yes, yes.
It seems to me that this formula of the velocity being proportional to the distance between the points,
Yeah.
in order to get there, you have to have your space, then embed it to a higher dimensional space.
Not necessarily. I just tell it, you see, in general relativity, you don't need to embed anything in high-dimensional spaces, you understand, because curvature is a local notion. I am embedding the things only, okay, to make it, to bring it at the level of elementary school, yeah? So, now, What is the geometry? What is Friedman geometry? Some people still now, okay, in some books, I don't want to say, struggle how to derive Friedman element and how to go from one coordinate system to the other coordinate system. At a certain point, actually, it was a really big deal. So, but I don't know. It depends on the people. For some, it was a big deal, but okay, nevertheless, I think at the time when Cartan wrote his papers about differential geometry, to speak about light element is not a big deal. So how can we get Friedman metric? Again, let's start with sphere. Let's think that we live in two-dimensional space. And let's embed this sphere in the three-dimensional space with so-called Euclidean geometry. Then if you will take 2 points on the sphere, because the equation of the sphere is x squared plus y squared plus z squared is equal radius of the sphere, right? Then the distance between 2 points on the sphere could be written down dx squared plus dy squared plus dz squared. But z here is not independent function, as you understand, because z from this equation is the function of x and y. You see? Now, if we will take this thing and differentiate it, then we will get that z dz is equal minus x dx plus y minus y dy. And therefore, from here, we can also write that z is equal square root of a squared minus x squared minus y squared. From here, we can express dz and substitute here. Then, for the distance between 2 points on the sphere, we will get that it's equal dx squared plus dy squared plus x dx plus y dy squared divided by a squared minus x squared minus y squared. So can you recognize here so-called Friedman metric or not? Perhaps not yet. For that, we have to go to more convenient coordinate. And instead of x and y coordinate, let's introduce in xy plane spherical coordinates. So we will write that x is equal a' cosinus theta, and y we will write as a' sinus theta. Then, okay, you know from here that x squared plus y squared is equal a' squared. So x dx plus y dy will be equal a dA, correct? So as then dx squared plus dy squared is, as you know, is dA squared plus a squared. So substitute this simple thing, and in your head you will immediately get the following form for the metric element. It will be dA' squared divided by 1 minus a' squared divided by a squared plus a' squared, and here you have d theta squared. So now if you will repeat the same procedure, but will consider three-dimensional sphere, which is embedded in four-dimensional Euclidean space, yeah? So, and then go to the spherical coordinates, then the only change in this formula will be sinus squared theta d phi squared. You see, so this is metric of homogeneous three-dimensional space with positive curvature, which is analog of the surface of the sphere. On the other side, you can consider the radius going to infinity. Then sphere becomes plane, correct? And then you see immediately that this term here disappears, and you are getting metric of three-dimensional flat space in spherical coordinate. Now, formally, you can consider only case when a squared is negative. What is wrong about it? Nothing wrong. Forget that you need to, okay, embed your surface in high-dimensional space, and then everything is perfectly fine here. There are no imaginary things which appears, and a squared smaller than 0 case correspond to third case, which we have so-called case of Lobachevsky space of constant curvature. But this space cannot be embedded in three-dimensional space, as I told, even into when it's two-dimensional. But nevertheless, it can be embedded in the space with signature plus, minus, minus, yeah? But it's, in fact, actually, I don't know, some people help with imagination, this kind of embedding, but I think it's not very useful. Doesn't matter, but the cases, the only cases, in a case of trivial topology or simple topology, which we got, are three cases which correspond to homogeneous isotropic case. And yes.
I don't understand something. We had the metric on the sphere.
Yes.
And we know that the metric on the sphere is not what it's written on the board. It's just without the without.
No, this thing.
Yeah.
Metric on the sphere is okay, this kind of thing, without this third term.
Yeah, but we had the metric on sphere.
No, this metric is in the flat space where we put this sphere, you see? So, in the place where we embedded this sphere, you have flat metric. But, okay, the induced metric on the sphere is not flat. You see, this is the difference. So, now, you could actually transform somehow coordinates, or you can introduce rescale radial coordinate, where you rescale the thing by the absolute value of a squared, and then metric, which you are getting in 3D case, looks like this one. A squared, and then here you have dr squared, 1 minus k r squared, plus r squared, and I will write here d omega squared, where omega is the line element on two-dimensional sphere of unit radius, you see? So it's the other useful form where k, in this case, can take three values. -1, 0, or +1. Clearly that this thing corresponds to Lobachevsky space, this is flat space, and this is space of constant positive curvature. Now, okay, there is one more good choice of coordinate which is very useful in the case when we learn something about propagation of light in these spaces, when you introduce, instead of this dr squared divided by this factor, new coordinate d high squared, yeah? So you claim that d high squared is equal to this ratio. Then after that you make integral, rewrite I in terms of high, and this metric can be rewritten down in the following form. It's r squared, then d high squared, plus here you have three possible cases which you have to write. So it's either sine hyperbolic high squared. This is the case of open universe, as you understand. High squared is normal case of the flat universe, and normal sine squared high, d omega squared, in the case of closed universe. So one of the things which you see immediately here, that closed universe, three-dimensional universe, has finite volume, because this high, in this case, is changing from 0 till pi, and then you cover the whole space. And you can calculate, similar to the surface area of the sphere, the volume, which is actually nothing more than surface area of three-dimensional sphere, and you will get that this thing, I think, is 2 pi cube, 2 pi squared a cube, as far as I remember. You see, now, how to implement evolution in this case? Of course, this is metric of the space at a given moment of time, and this given moment of time, okay, we took according to the following principle. We said that the time everywhere is the same, where at each point you have the same energy density. So it's preferable choice of coordinate system. And in fact, actually, it's a good choice. Principle, you could describe electric, of course, in any coordinate system, but since Copernicus, nobody describes the motion of the planet using Ptolemy's system, right? Therefore, let's not make headache with it. So how to implement evolution? Evolution can be implemented, in this case, when you want to preserve homogeneity and isotropy, only in one way. You have to assume that the scale factor here depends on time. You see? Because otherwise, you would deform the properties of the space. Now, so A of t is the only possibility when you want to preserve homogeneity and isotropy. And in this case, you could write also interval in general relativity, distance between two events, which is nothing more than difference dt squared minus special distance between 2 points minus this element, a squared of t. And then here we'll write d high squared plus phi squared high, okay, where phi squared is one of these three functions, d omega squared. And you understand that the evolution of the whole homogeneous universe from the point of view of geometry is characterized by one function which is called scale factor. What can be more simple? Nothing, right? Also, if, for instance, there would be no matter in the universe, then the only solution of all these equations would be Minkowski space. But if there is matter, then the only distribution of the matter which is compatible with homogeneity is isotropy is the distribution when energy density depends only on time. And because we are considering huge scales, as you understand, for gravity relevant only huge scale, then description of the matter from the point of view of hydrodynamics, like this one, is enough for everything in principle. You do not care from what this matter consists, with one exception, as I said. Now, what is the other property of the matter which could be relevant in general relativity? Of course, pressure of this matter. And this pressure normally is given as a function of energy density. I repeat that it's given because it's determined by microscopical physics. And this dependence of pressure on energy density is called equation of state. What are the examples of equation of state? If we will take everybody here in this room, yeah, including us, and we'll ask question, what is our pressure from the point of view of general relativity? What would you think? 0. So for us, it's approximately equal to 0 from the point of view of general relativity. What is the example of some matter for which pressure is not equal to 0 from the point of view of general relativity? We have this example also in this room. Light, yeah. So for light, pressure is equal energy density divided by 3. These are two most important things because, as I said, okay, pressure is equal to 0 for baryonic matter from the point of view of general relativity. It's equal to 0 for dark matter. Then we have radiation in our universe with this equation of state. But also we have one more important case, dark energy, for which pressure is equal minus energy density. You see? Now, we have two functions. Therefore, we have to have two equations to describe how these functions are developing. Let's consider first case when pressure is approximately equal to 0. And let's apply just Newtonian theory to derive equation. So, let's assume that our universe is homogeneous isotropic. Then, okay, if space would be infinite, what would be Newtonian potential at each point? If you would have homogeneous distribution of the matter around the space, but space would be infinite, Newtonian potential would be infinity. You see, in spite of the fact that you wouldn't expect here, okay, any kind of things, but differentiate infinity. Therefore, even for Newtonian consideration, we have to have some kind of general relativity justification. And what is general relativity justification? Let's take and make whole and remove matter in this homogeneous distribution. Then what will be the metric inside this whole? Minkowski metric according to so-called Birkhoff theorem, because it's spherically symmetrical case. This thing means that you can remove everything within this ball, and the whole dynamics of this ball will be decided by the amount of matter within this ball. Let's take probe particle on the body of this ball. Of course, radius of the ball as a function of time in homogeneous case will be scale factor multiplied by chi, where chi is constant of integration, yeah? So let's write for the probe particle here, second Newton law. So mass multiplied by acceleration of this point is equal to the gravitational force which is acting on this point. And what is gravitational force? Is gravitational constant, sorry, I will make exception, mass of within this ball of the matter multiplied by mass of the probe particle divided by r squared. Newtonian law. I hope that people still didn't forget this. Now, let's do the following thing. Let's multiply it by r, divide by r, and write here 4p divided by 3, and also here 4pi divided by 3. So I did nothing. But why I did this nothing? Because if you divide mass by these things, then what you will get? This is volume, 4pi divided by 3r cubed, mass divided by volume, nothing more than energy density, right? Now, if you substitute now that r is a multiplied by chi, then here it comes r and here it comes r, chi will drop out, and what you will get mass also here is cancelled, you will get the following equation. A2 dot is equal minus 4p g over 3 epsilon multiplied by a. So it's so-called one of the Friedmann equations, which is exactly valid also in general relativity. If you would take now equation, Einstein equation, would substitute in Einstein equation this metric, and will take energy momentum tensor for the perfect fluid. You remember this energy momentum tensor or not? For the perfect fluid, it's written everywhere, okay, not only in Landau-Lifshitz. So it's like this one, P delta mu nu, where P is the pressure. How you write normally energy momentum tensor? You claim that it's second rank tensor, which is symmetric, and dt over dx with indices mu is equal to 0, give you equation of state. Not equation of state, but equation of motion. So like earlier equation in this particular case. Now, if you would take now this energy momentum tensor, substitute it in Einstein equation, this equation would be modified only in very simple way. Okay, there come here 3 pressure multiplied by scale factor. So you see that in general relativity, not only mass, but also pressure induce gravitational wave on completely equivalent democratical principle, with exception of these 3. You see which violate a little bit democracy. But now, other thing, okay, which we need other equation, is so-called equation for the energy density. Here you see immediately from this formula already that in the case, in the case when pressure is equal to 0, you can write immediately energy density, right? What is this? energy density in the case when pressure is equal to 0 is mass divided by volume, okay, which depends cube. Or it's 1 divided by a cube, proportional to 1 divided by scale factor. So this fact is nothing more than just the law for the conservation of the mass. Now, let's take the whole thing and let's differentiate it. Why I differentiate it? Because I want to rewrite this conservation of mass in the form when it will be easy to generalize it for to the case when pressure is not equal to 0. Then you will get that epsilon dot is equal minus 3h epsilon as a result of this simple differentiation. Now, if you want, you can write here constant divided by a cube. Now, how this law is generalized when pressure is not equal to 0? Again, very easy. You write here epsilon plus p. Why? Okay, it's so, and how can you understand it? Of course, it follows from Einstein equation, or better to say, okay, if you will take divergence or derivative and divergence of the energy momentum tensor, you will get immediately this equation. But this thing also could be understood very easily, because if you consider ball with a pressure which is expanding, yeah, then pressure makes the work. And the change of the energy density is equal minus pressure change of the volume. So first law of thermodynamics, in spite of the fact that, of course, you have no right to apply it here, because everything is out of thermodynamic equilibrium. Nevertheless, it's a good hint how the things work. So you know that volume is proportional to a cube. You know that total energy is energy multiplied by a cube. Then, okay, take these differentials, and you will get immediately this equation. So we have two equations for two variables. Is it enough or not? Question. Or we will miss something in general relativity. I can leave as exercise, take these two equations, and make the following thing. Find the first integral of this equation. So multiply it by a dot, etc., and then make integration of this equation with using this equation of state. And then equation which you will get will be like this one. So first integral of these two equations will be h squared plus some constant divided by a squared is equal 8pg over 3 energy density. Pressure, by the way, will not be entering this equation, but this equation is nevertheless valid for an arbitrary equation of state. So this thing you would get as a result of this integration, but there is no hint of the geometry here, nevertheless, right? And this constant of integration could be arbitrary constant. If theory would not be geometrical, then of course you could take this constant as you want. But in case when geometry is not flat, radius is the radius of curvature. And if you would take 0, 0 Einstein equation, so-called constraint equation, it will fix you this constant of integration to be equal k, where k can take value 0 or plus minus 1. You see? So if you would take this equation together with this equation, everything is fine. If you take this equation together with this equation, everything too is fine. But if you will take these two equations, that is not enough to determine the problem. Now, h, by the way, I hope you didn't forget that it's a dot over a squared. Now, okay, good. So now we have everything. This thing is normally called Friedmann equation. And now we can describe different cases how when universe is evolving. And let's consider the most important cases. So, first of all, let's consider, now I will use Planck units, okay? And G will be equal 1. Let's consider first case when pressure is equal to 0. Okay, now, in this case, energy density can be written down as some constant divided by a cube, as you see from this equation, or it's conservation of mass anyway. So now let's take this thing and let's substitute it here. So h squared is equal plus k divided by a squared is equal 8p g over 3g, I promised I tell, a divided by a cube, yeah? Now, first of all, you see here, also let me write like this one, phi pg over 3 epsilon. If you would be asked to determine what is our geometry today, how you would do this thing? You could use in principle this equation. Because Hubble constant today you can measure. Let's assume that you found that it's h squared plus k divided by a squared is equal to 8pg over 3. And energy density you could measure, right? So you measured energy density. Now, when you have this number and this number, what can you say about geometry? If this number, h0 squared, is larger than 8pg over 3 epsilon, yeah, then k should be negative, of course. Yeah, you could introduce, build from h, the quantity which has the same dimension as epsilon. It will be so-called epsilon critical, which is 3h0 squared divided by 8pg. You see, so if epsilon 0 is larger, smaller than epsilon critical, and epsilon critical is nothing more than just kinetic energy, which you characterize with the help of energy density of Hubble expansion. Then k is equal 0, the k is negative. So you see, very easy to determine by measurement the curvature of our universe. If this kind of thing, epsilon critical is equal epsilon 0, then curvature is 0. So our universe at the given moment of time is flat. But by the way, it doesn't mean that the space-time is flat. Because what plays the role in general relativity is the curvature of space-time. And in the curvature of space-time also h contributes. You should not forget about this thing, because I remember that in '81, okay, when Hawking was in Moscow, Linde and Hawking had one weak argument. Hawking was saying that inflation predicts flat universe. Linde was saying that inflation predicts flat universe also. One was happy with the statement, the other was unhappy with the statement. And Hawking meant that flat universe is Minkowski space. And Linde meant that it curves space-time, but nevertheless, okay, it has flat geometry at the given moment of time. So, okay, for this kind of stupid misconceptions, they have spent 1 week. At this time, of course, communication with Hawking was much easier, but nevertheless, okay, you needed to have the patience of Andrei, yeah, for this important thing. So, if epsilon 0 is larger than critical energy, then universe would have positive curvature and the volume would be finite. And in this universe, you could go in this direction, go, and then would come to the same point from the opposite direction. Now, this kind of relation between epsilon and epsilon critical, people characterize with the help of so-called cosmological parameter, which is epsilon in the matter divided by epsilon critical, which characterizes the rate of Hubble expansion. And one of the predictions of so-called inflationary cosmology that this omega 0 should be equal 1 with the accuracy 10 minus 5. You could think, I will explain why, that what kind of triviality is this? But it was not triviality because, okay, one thing is our wishes and the other thing what nature tells us. If you would tell to astronomer in 1980 that omega is 1 or even larger than 1, he would look at you, okay, with sorrow. He would think that you are a client for psychiatric clinic, yeah? Because, okay, at this time, people could not get more, okay, with all efforts than 0.02. You see? Because there was not even known this gas in the clusters. Now, but there were people with courage. Of course, Zwicky had a lot of courage. People also at this time, okay, was making so-called non-equilibrium virial theorem, and also he found that omega is 0.2 because there is a lot of matter in the gallows of the galaxy. And by the way, it was in agreement also with all these rotational curves. But as you understand, the arguments were not 100%. Now, in 1995, for instance, there was much more precise measurement of large-scale structure of the universe and, okay, virial dynamics of the clusters, but maximum what people could get 0.3. You see? And my good friend Andrei Linde became so panicked that he started to write papers about open universe. I told him, okay, Andrei, don't do it. But he didn't listen to me, and when I wrote some paper against this open universe, after that we didn't talk to him, okay, at least for a month to each other. So you see, scientific thing went. So then I told that they will find the thing, don't worry. And in 1998, if you remember, this missing 70% of the energy, okay, was found in this measurement of supernova. So the things came in the place. After that, I remember that, okay, we had dinner with Mössbauer, you know, this famous Mössbauer. And then he told me, but omega is equal 1 is triviality. I told him, okay, come on, now it's triviality, but you see, it was not like this one 5 years ago. Then, other interesting thing that after this result about finding of dark energy appeared, Scientific American came with a paper on front page, inflation is in trouble. So, you know, these people managed to recall or to rename triumph of inflation in trouble of inflation. Why? Because inflation didn't predict the existence of dark energy, but you know that actually it was not obligation of the inflation. Inflation was predicting that omega equal 1 just on the basis of simple kinematical argument. But okay, I still have 5-10 minutes. Let me go a little bit further with, I don't call it mathematics, okay, it's arithmetics. A little bit further, and let me find solution. Where is, huh? Where did I put this? Ah, okay, I found both are here. So let me go a little bit further with this calculation. First of all, okay, if k is equal to 0, then it's very easy to solve this equation, right? No trouble. But even if k non-equal to 0, let's consider the case when scale factor is very, very small. So very early universe, yeah, when it was very small. Then which out of these two terms dominating? When a is very small. It's clear that this term could be neglected in very early universe anyway, right? And then solution, which you will get, again, using this a dot over a squared Russian style estimate, yeah, 1 over t squared, which you are getting for scale factor, is a proportional to t in power 2/3. You see, it's so-called normal decelerated solution. And if you will look at this equation, then from this equation it follows that pressure is equal to 0. So second derivative of scale factor is negative, and gravity in a normal way decelerate your expansion. Let's take and estimate what is the energy density in this particular case in very early universe. It's again very easy, because if you forget about k over a squared factor, then you will get that energy density is equal 3h squared divided by 8p g, yeah? Now, from here it follows that h is equal 2 over 3, 1 over t, because h was a dot over a. If you substitute it here, what you will get? You will get, what you will get? I think 1 divided by 6p t g squared. So this is anyway, in very early universe, how energy density depended on the moment of time. And from here, okay, because, for instance, if you will take radiation, yeah, then for radiation, you know that the temperature, energy density is proportional to the temperature in power 4. From here, in very early universe, you can relate moment of time and temperature. And from here also it follows that at very early moment of time, temperature was huge. Now, but when temperature was huge, how dynamics was developing? You know this equation, epsilon dot is equal minus 3 h epsilon plus p. A. Yeah, epsilon. Now, let's set, instead of pressure for radiation, epsilon over 3. Then, okay, integrate this equation, what you will get. How energy density is changing in this case? 1 divided by scale factor. In which power? Okay, here was 3 when pressure was irrelevant. So it's 1/3, yeah, of epsilon. Now, 1 plus 1/3, 4 over 3 comes minus 4, right? So you could suspect, even without solving, but you can solve that it's 1 divided by a in power 4. So energy density in the universe, when, okay, for radiation, energy density grows faster when you go in past, when scale factor is smaller. And by the way, how to explain this kind of law, 1 over a4? You see, number of photons is conserved, but every photon, okay, when it's in the box, for instance, becomes red shifted or blue shifted when you go in past. Therefore, okay, a 1 over a cube is because the energy density of photons is dropping, and 1 over a is because of the redshift. Now, how in this case, for instance, universe is evolving? What is the dependence of the scale factor? The dependence of the scale factor, okay, is again h squared proportional 1 over a fourth, h squared by order of magnitude 1 over t squared. So a from here is proportional to t in power 1/2. You see? If you would take arbitrary equation of state pressure is equal W energy density, where W would be constant, then you would get, in this case, which law for the evolution? You will get, okay, 1 divided by 3, energy density would be proportional 1 divided by A3, 1 plus W. And then for an arbitrary W, you can find what will be the change, okay, or time dependence of scale factor on time. Now, let's consider what I called very special case when pressure is equal minus energy density. In this case, what is W? Minus 1, right? When pressure is equal minus energy density. Look at this formula, 1 plus WY. Okay, so dependence on scale factor in a case of equation of state pressure is equal minus energy density disappears. Energy density remains the same. So what does it mean? That this quantity is constant. So, and this is, okay, equation of state which correspond to cosmological constant. It's not changing with time in the past. Now, let's assume that energy density is proportional 1 divided by a in power alpha. Alpha is still unknown. Alpha is equal 3 for the case of dust and equal 4 for the case of radiation. And for the case of cosmological constant, it's just 0. Now, what will be the solution of equation for scale factor in this case? Okay, again, the same story. Yeah, it's 1 over t squared because it's nothing more than h squared. So you are getting that A is proportional t 2 divided by alpha. Now, when alpha is 3, is fine. You have decelerated expansion because it's t in power 2/3, right? When pressure is equal epsilon over 3, then you have alpha 4. It's again decelerated expansion if you calculate second derivative. But when alpha is smaller than 2, yeah, then, okay, A is proportional to t in some power which is larger than 1. And, okay, if you calculate second derivative, you will find the second derivative is positive. So it's accelerated expansion. Alpha is equal to corresponds to the case when pressure is equal minus energy density over 3. Correct? So, if pressure is equal minus energy density, alpha is 0, you are getting t in power infinity. And what is t in power infinity? In normal cases, because you cannot have infinity, is nothing more than just exponent t. Yeah? So you are getting thus exponential expansion. And you can check it very easily. Now, what happens, okay, with this kind of change of the regime? To understand this thing, you have to look at this equation. What determines your acceleration or deceleration? This combination epsilon plus 3 pressure. When epsilon plus 3 pressure is larger than 0, people call it energy dominance condition. By the way, under this condition, Hawking and Penrose proved theorems about singularity. Then gravity is attractive force, and you have decelerated expansion. Somebody gave initial velocities, and then gravity was only decelerating the expansion. But when energy density plus 3 pressure is negative, then you have here minus, you have here minus, and good thing about 2 minuses, then when you multiply them, they give you plus. And instead of decelerated expansion, you are getting accelerated expansion in this case. So it's extremely easy. Now, but for that, you have to have equation of state. For instance, pressure is equal minus energy density, because in this case, this combination is equal minus 2 energy density. By the way, people always assume that energy density is always positive in physics, with one exception. Who knows this one exception? It's anti-de Sitter space, you see, about which everybody is so lucky, but nevertheless, it's exceptional case. When in other cases people meet negative energy densities, and they think that it's strategy, but here it's okay, because it's still homogeneous. Now, okay, after that, where to get these kind of things which could make from gravity anti-gravity? First of all, we know that it's already in the nature, because otherwise why people got Nobel Prize? It's not quite clear. So on the question, okay, why cosmological constants dominate today, there is a very good answer. Because God wanted to give us hint how he created universe in past. If today is possible, why not in past? Right, second thing, how to get this equation of state? From the point of view, okay, tomorrow, because now it's 2 minutes and you are tight, perhaps I'm also. So, not tomorrow, when I teach next time, I forgot already, but doesn't. Next lecture, yeah. Or I still have 2 minutes, I will give you. Very little hint, you see? So, it's also very easy, I don't understand why people didn't get it before. So, let's take scalar field. After that, I will read of scalar field and we'll speak about equation of state, yeah, mostly. Because you know that we are considering really gravity in large scale. Therefore, macroscopical physics is important, but up to a certain extent in these cases, just giving us exotic equation of state. So what is scalar field? Is some kind of thing which satisfies this equation of motion. You see, now you remember the definition of the energy momentum tensor. D over dx, let me skip indices, should be equivalent to this equation of state. And it should be symmetric. This allows us to fix energy momentum tensor. And from this requirement, I can write immediately energy momentum tensor for scalar field mu nu in the following form. It will be epsilon plus p u nu minus p delta mu nu. Of course, you can tell me that I'm crazy that I'm writing this thing, yeah? But let me define. I still didn't define what is epsilon p here. Epsilon here will be 1/2 phi gamma. So it means derivative with respect to x gamma. Phi gamma plus v. This v which comes here as potential. P here will be 1/2 phi gamma minus v. So you see, if you will substitute these definitions, as I would say, here you would get what people normally write for the energy momentum tensor of scalar field. But you can use this analogy because we learned how universe behave, yeah, in the other cases, just to get out what scalar field can give you. U I want to define, but it's irrelevant. Okay, let me write. U alpha is equal phi alpha divided by square root of phi gamma. So these kind of things goes only if phi gamma is positively defined. But this is the case when you take, for instance, homogeneous scalar field, because you don't want to spoil in homogeneity. Then in this case, energy density becomes sum of time derivative of scalar field squared. It's like kinetic energy plus potential, and pressure becomes 1/2 phi dot squared minus potential energy. Now imagine that you can realize the regime when phi dot squared much smaller than v. Then in this case, you can neglect these terms here. And what is the equation of state you are getting? Pressure is approximately equal minus energy density. If you forget about potential, what equation of state you are getting? Pressure is equal plus energy density. You see, and I can arrange you whatever you want here. Therefore, it's very legitimate to consider in the universe all equation of state, okay, like pressure is equal W energy density, where W is in the interval between -1 and +1. And anyway, you can describe it with the help of scalar field, yeah.
Pressure equals minus energy is a very particular, special form.
Yes.
Because it doesn't pick out a particular frame.
Yes, great.
All the other forms pick out a frame.
Mm-hmm.
So the way to just define cosmological concept is it's the only form of energy in a vacuum, which is not an ether, no preferred.
Yeah.
And any other such assumption picks out.
Right, but I tell you, very good. What you see here is the question up to what extent pressure is precisely equal energy density is useful. At minus energy density. Today, very good, okay, contradicts nothing. But in past, completely useless, because you see, it will stay constant all the time. Of course, the space which you will get also will be not only spatially homogeneous, it will be also time translationally invariant. But what is important for anti-gravity is not precise equality, but approximate equality And moreover, this approximate equality, it should be approximate, is responsible for finishing this stage of accelerated expansion. By the way, okay, I was amazed, but now I recall that Zelidovich was always stressing at the beginning, of course, I was following David principle, shut up and calculate. So, okay, in old days I was just sitting without speaking and calculating. Yeah, but Zelidovich, okay, spoke besides of this thing. And therefore, he was always stressing that inflation, which is useful, not useless inflation, which leaves something after it, is inflation or de Sitter stage, quasi-de Sitter stage, with broken time translation invariance. You see, this breaking of time translation invariance for the de Sitter is one of the basic ingredients, by the way, which will have important prediction for our measurement. You see? Because constant would always stay constant. It would be nice accelerated expansion forever. You see, but who cares? Because nobody even would ask the question what happened before. So, okay, but this is the point when I am ready to go to anthropic argument. Okay, let's stop. Okay. Yeah, you see. Okay. In fact, everything what we have to have for inflation, okay, have to happen as the energy densities which are 12 orders of magnitude below Planckian density. Why? Because amplitude of perturbation 10 minus 5, 10 minus 6 is precisely square root of the ratio of the energy densities. If I will take, for instance, high order corrections as just corrections like R squared things, then of course they are negligible. 12 orders of magnitude. On the other side, because you know that, for instance, if you will not even quantize gravity, you know that in external background, okay, theory is renormalizable only if you add R squared terms there. In principle, you could start with this term with the, how it's called, arbitrary coefficient. And then, without thinking about scalar field even, you could make this coefficient in front of R squared 10, 12, and could get perfect inflation, which would be not worse than all these thousands of the scenarios. And in fact, it's even better because it has actually very smooth, graceful exit. And by the way, this theory, okay, was written in 1780. In fact, actually, first time calculation of the spectra we did in this theory because all this particle physics scalar field still were not known, yeah? Because first time spectrum of calculation I calculated with this logarithmic stuff in 81 in R squared gravity. But you understand that it's legitimate theory with all the same predictions, which by the way are equivalent predictions to so-called Higgs inflation. And it's one of the models. But as I will try to stress that, okay, learning about this kind of scenarios, particular scenarios, we cannot learn too much from observational, from observation. Because, okay, what we are measuring? We are measuring 3 parameters. In fact, deviation of equation of state from n equal 1. We are measuring energy density, and it's all. So, therefore, I always recall anecdote when inflation started, because you understand that, okay, when particle physicists didn't care about inflation, okay, it was published, etc., etc. R squared particle physicists